just give it.
Like what? We only have like one. Oh wait, do we have more? Oh, we have more. We have like two.
Yeah, there's two groups sitting here.
They'll figure it out. Don't you worry. Don't you worry, darling. They'll figure it out.
So, if you want some other subject to go first, all set up? Oh,
It's fine now? Nina, take.
is the mic on? Hello, am I audible? Okay. So, before we get into the answer to this question, I'd like to just cover some common problems that a lot of the teams seem to be having. Hotspots are not regular volcanoes. A lot of you, so this question basically deals with hotspot volcanoes. Now, in the participant briefing as well, we had mentioned the fact that there are volcanoes that are associated with tectonic plate boundaries, and that is where you'd most likely find a volcano at all. But these hotspots are special volcanoes that are found in the middle of the plate, right? So, and the question here was actually dealing with the ruthenium concentration of the rocks obtained from the hotspot volcanoes as compared to the rocks obtained from any other volcano across the world. With that, I'd like to get into the answer for the first question. Would you like to present the answer? And then I'll just,
Yeah, so as you can see in the graph, the question's hypothesis was that this would be separated purely by gravity. But if it was separated purely by gravity, you would expect this orange line to fall further and further beneath the blue line for heavier and heavier elements. But you can see that it's not true for specifically the rare earth elements, the F blocks, some of the radioactives, uranium, this group over here. So you were expected to conclude that no, it does not support the purely gravimetric hypothesis. And this happens because in the, do you want to explain this actually? Yeah.
basically, the conclusion that we wanted you guys to draw is from 11th and 12th grade chemistry, which is the fact that these particular elements that you see here, they're D block elements with a high affinity to form alloys or just be able to associate with iron. And as the combination of these elements forms, it's a very dense material that moves to the center of the earth. It's not just the density of the element itself. Other than that, a lot of you were confused about which elements are P block elements and which elements are F block elements. So 51, I believe, no, somewhere around the 60s to 70 range is all F block elements. And they have a high affinity for oxygen. So this peak that you're seeing over here is because they can combine with oxygen, and oxygen is present primarily in the crust. So you'll find them there in the crust itself.
Now, for smaller planets, they would have a smaller surface area proportional to r squared, but they'd also have a much smaller volume, r cubed. So the surface area to volume ratio would decrease with increasing height. So larger planets would have a larger heat content, and they would take longer to cool, which would give the alloy that he described, time to move into the core. If you had a very small planet that would cool quickly because of what I just said, the elements would not have time to move into the core, and so you would have a bulk composition that is similar to the crustal composition. Now, the rocks studied here, they have a higher ruthenium level than just like normal non-igneous rocks, but also other igneous rocks that are found by normal volcanism. So from this, you were expected to conclude that this originated deep in the mantle, as opposed to other rocks that would originate from the top layer of the mantle. Um, so yeah, it originates deep in the mantle near the core. Um, and any places on Earth, you're standing on one. The Deccan Traps were formed by hotspot volcanism 66 million years ago, something like that. And Hawaii is a current place that is undergoing hotspot volcanism, so is Iceland, but there's other factors at play in Iceland. So yeah. Thank you, I hope you had fun. Yes.
So, what exactly are you trying to say? Okay, so that is a very interesting phenomena in earth science called a mantle plume. Okay, uh, if you don't mind, I'll get a bit technical with this. So there's a boundary layer between the outer fluid core and the solid mantle, which is called the DD dash layer. Okay, and from this DD dash layer, because of convective anomalies at the mantle on top, you get this decompression factor deeper within the earth. Any other questions? Thank you.
I would now like to call Yashika from the maths question making team and Parth Sarda also.
Okay, so hello everyone. I think a lot of you answered the winning strategy, like the condition on n correctly, which was that n should be a non-Fibonacci number for the first player and a Fibonacci number for the second player. Now, if I write the Zekindorf representation of, let's suppose, any n, then I get something of this sort. Now I claim that the optimal strategy to win is that I'll remove the smallest number in the Zekindorf representation. Now to show this, that this is the optimal strategy, I'll divide the proof in two parts. First, I'll show that from any winning move, you can lead up to a losing position. And next is that all losing moves lead to a winning position. That means that in order to get to a losing position, you would have to be in a winning position at the start. So for the first part, which is that any winning move will, like all winning moves, have at least one path with, using which you can go to a losing position. Oh, also, what do I mean by a winning and a losing position? So let's define m comma n. Now this is the maximum number of florins that I can pick from my pile, and n is the last term in the Zekindorf representation. So in order for this to be a winning position, m should be greater than or equal to n. That means my limit should allow me to pick the last term in the Zekindorf representation.
Last term is the lowest.
Huh. Also, these are ordered as in the last term is the lowest term. Right? So now, since I know that this is a non-consecutive unique representation, if I can write any Fibonacci number as this, and this means it's strictly greater than 2fk. So if I pick the smallest term in the Zekindorf representation, then my opponent cannot pick fk plus 2 because it's non-consecutive, like the terms are non-consecutive. That means this isn't in the limit. It's clear? So that means from any winning position, I can find at least one path that goes to a losing position. Now, second, what I'm trying to prove is that all losing positions always lead to a winning position. That means I all have to prove that if I have a losing position, that must have originated from a winning position. So let's suppose I have something of this sort, and I go here, and this is a losing position. That means Does anyone have any doubt? Okay. So if I go here, this is the losing position. That means the last second of term of this is greater than this, which means all the terms in the second of representation of this are greater than this. So what I can do is, if I look at the second of representation of x and that of z of n minus x, I'll realize that they're completely disjoint. No terms intersect, right? So that means I can just concatenate them, and I'll get the second of representation of n. Now, in order to go from this to this, I must have took out the last few Fibonacci terms from the second of representation, since there is only a unique representation. And this implies that my x was within the bounds of n, which means I started from a winning position originally. So the only way this will fail is if at the start you have a Fibonacci number where you cannot follow this strategy. So the strategy is, if it's a non-Fibonacci number, the first player can always win. You just write the second of representation and subtract the lowest term. So that's it. Does anyone have any doubts? Thank you.
So as Yashika pointed out, this will happen because you'll be having a contradiction here. So this will basically imply that your m was greater than t. I'm claiming this to be the final Fibonacci number. So at the end, you cannot go from a losing position to a losing position. If you're at a losing position, you'll always go back to a winning position. Just reiterating the point she made. Thank you.
Now I would like to call Govind from the biology question making team to present the solution.
Am I audible? Am I audible? Okay. So the first question was about basically the main difference between population 1 and 2 is that you can have recombination in the first population because multiple different genomes are infecting the same host cell, and that allows you to recombine different genomes. So this is basically a sexual population versus an asexual population, and the question is, just considering how the populations would deal with mutations, why would Ninad's hypothesis that the first population would show more rapid increase in fitness is true? Like, how do you justify that? And the answer is that I think two of the teams got this, but with respect to beneficial mutations, if you look at an asexual population, if different beneficial mutations arise in two different individuals in an asexual population, there is no real way to bring them together because they're never going to recombine. So the only way you can have a genome with both the beneficial mutations is you have to wait for that exact mutation to occur on one of the genomes. So, but in the case of a sexual population, that is population 1, this is possible within a single generation, where if you have these two individuals, they can recombine and you can create like a much more fitter strain. With respect to deleterious mutations, in the asexual population, like an entire lineage without any mutations, if it's lost by chance, there's no way for you to back mutate because, again, there is no recombination here, so you can't really get a strain back. So what ends up happening is that the asexual population ends up accumulating mutations, which eventually causes a massive decline in fitness, which is this concept is called Mueller's ratchet. So that was the first question. The second part, I think, I think teams got this, but the question was why. So you observed that this hypothesis turned out to be false. You didn't explain your observations, but you observed that. When you look at the fitness payoffs when M0 and M1 interact, you see that when alone, M1 does worse than it does with M0, and the opposite for M0. So that happens because, like some of you said, the M1 strain, because it has evolved in an environment where it has multiple other genomes to compete with, it has evolved to become more prolific at competing, or to put it better, using the growth factors created by other individuals and using it for itself. So, so there's a mention here about using the genome does both of these functions. So the M1 strains, the M1 mutants would preferentially allocate more time and resources to act as a act for replication rather than for the ribosomes to translate it, because it has other individuals in its neighborhood that is producing the growth factors for it. This thing is called a public goods dilemma in game theory. It's where you have a good that every individual in the community contributes to, but anyone can use it regardless of whether they are paying for it. And what happens in population 1 is that why it doesn't keep increasing is that at some point you are going to reach a frequency of cheaters, like M1 is a cheater here, that now there's a fraction. If you go below this, there won't be enough individuals producing the growth factor, so the population as a whole is going to suffer. So that's why you don't see a greater increase in fitness. The answer to 3 is that now as opposed to M1, M2 has evolved in complete isolation. So inside in the M2 lineage, inside any host cell, all the virions are clonal offspring of each other. All of them are identical. So there is no impetus for these individuals to cheat, because there's no difference. So these, and because they're grown in isolation, this strain has grown to become more efficient at sort of hijacking the host machinery, both replication and translation, and just become overall fitter. And so the fitness, so as you would see, the fitness of M2 is much higher than M0. So it basically becomes fit to the point, it becomes so good at what it does inside the host cell that it is able to afford being cheated on by the cheating strain M1. So that's why you get that fitness table. And as for the observation about how a population of M1 and M2 evolve, you would see that in the Y1, the M1, M2 graph, you see that at some frequency, the frequency of M1 is equal to M2. So you're supposed to infer that at some frequency of M1 and M2, they can exist in stable equilibrium. Whereas in the case of M1, you can see that for any frequency of M1, it is fitter than M0. So you're always going to reach fixation of that mutant. So yeah. Any questions?
I would now like to call Anurgho from the physics question making team to present a solution for the physics brief thought.
One more, sir. Yeah, so let me first start off by clarifying that the question mentions that the initial conditions of the universe have perturbations in the matter field as well as the potential, which means that there'll be certain overdensities and underdensities. If it was a completely homogeneous universe with the exact same density of matter and potential everywhere, there would be no dynamics at all, and it would just remain the same for all of eternity. That's not the case here, and that is why it's interesting to track the dynamics of the system. So again, this was my first point. The second point of importance is that if there are perturbations in the potential that's sourced by the matter distribution, and these are uneven, so if the potential looks something like this, then there'll be so if there are particles that don't have a lot of random velocities in magnitude, they will sit at the bottom of these potential wells. And particles that arrive at the bottom of these potential wells will have a nonlinear effect. That is, that they would increase the depth of this potential well and in turn attract more particles. So there's like a nonlinear feedback that's happening. And since we have mentioned in the question that there is a fixed number of particles in this universe and no annihilation or production is allowed, particles that started off in sort of voids, that was under densities, those under densities would become even less dense, and over densities or regions of higher density on average would become higher in density. So this nonlinear effect like goes on. Now for the main idea of the first question is that how would you know when the matter that falls into one of these potential wells actually stays in the potential well? Because that is the condition for gravitational binding. And the correct physical quantities to compare here are the kinetic energy per unit mass and the potential, the depth of the potential. So if you compare the V square with the phi, I hope these notation is clear to everyone. If there's a doubt, please ask. If this condition is satisfied, then there is no chance that a particle would stay in this potential. They would come out, and that is when it sort of free streams, that it's not gravitationally bound. On the other hand, if this condition is satisfied, then this is the only circumstance in which the particles will stay bound. Now on average, in universe 1, the average thermal velocities are smaller in universe 1 compared to the second universe. And hence, there'll be more particles satisfying this condition compared to this condition. And hence, this is how you argue correctly that there'll be more structure formation or more gravitationally bound objects in the first universe compared to the second universe. Note that these are dimensionally correct quantities to compare, and you can only compare quantities that are actually like dimensionally correct. Okay, so the first part is clear, right? So the first question. So there'll be more structure formation in the first universe compared to the second one. The second part of the question asks us to plot P of R, which is P of R is the probability that you'll find at least, that you'll find a halo of, which is a gravitationally bound object of at least radius R. Now the first thing to realize that P of R is a probability. So it can have a maximum value of 1. And where is that maximum value? If you consider the edge cases, that at R equals 0, what does that mean? So physically, if I spell it out in English, it means what is the probability of having a non-zero radius gravitationally bound structure, which is essentially every structure. So that should be, I hope this plot is visible to everyone. So that at R tends to 0 should be 1. Now, let me look at the other end of the axis. What at P infinite, R tends to infinity, which is basically asking the question, what's the probability of finding a halo of at least R that's just infinite, which is obviously, as R becomes larger and larger, it's 0, because there can be just finite mass in the universe, and that can be finitely bounded. So this goes to 0. This is true. Note that this is true. This limiting behavior is true for both of these universes. Now you have to compare what happens in the middle. Now for universe 1, suppose it looks something like this. Universe 2, we have said, will have lesser bound structures. And so the rate of finding these large halos of say a given R will also be lower compared to universe 1. So if this yellow chalk is universe 1 and this pink chalk is universe 2, it will look something like this. I hope that is clear. So I hope that is clear. Any doubts? So if I want to elucidate my final argument, is that given a certain R, which one of these universes will have a higher probability of getting halos of that radius R on average? Obviously, it is. Am I flipping the order? No, oh, it's fine. Yeah, on average, it will be 1. Oh, sorry, I thought 2 was yellow. Okay, yeah. Is that clear? Any doubts? Yeah. Oh, you have a doubt.
I'm just
okay.
asking
Sorry.
you to
Why?
yeah.
So consider any given radius R.
Yeah.
So So you understood the point that there'll be larger halos in universe 1, right?
Yes.
So on average, if someone asks you this question, what's the probability of finding halos of a given radius r? Which probability is higher in, like, the probability is higher in which universe? In universe 1 or 2? On average in universe 1,
Of a given radius.
for given radius. You do it radius by radius, right? At every bin. That's how you draw plot.
Yeah, yeah.
So at any given radius r, you ask yourself the question, okay, I have this universe having this many halos, which is more clumpy, so to speak, and this universe which is less clumpy.
Yeah.
So where will I find larger halos of this particular r if I do the counting manually?
That depends on the radius, right? Like
But more clumpy as in larger halos, right?
yes. So for larger radiuses, you
The
will.
probability will be larger for universe 1. That's what the plot shows.
Yep. This is an accumulative plot.
I think the color isn't very visible from here. The 2 is the lower one.
Yeah, yes.
Is that fine, or do you want more elucidation? I think that's fine.
Now I would like to call Vatsal from the Okay, Raunak from the chemistry question. Both? Okay, both. Okay. Vatsal and Raunak from the chemistry question making team.
Yeah, so the model that we described for our super atoms, as almost all of you pointed out, was very similar to the Thomson plum pudding. So in the potential energy term that we asked you guys for, this, it will actually have three terms. One for the electrons repelling each other. You have like n electrons, they repel each other. You will have that term in the energy. Then you will have one term for the assembling the positively charged cloud or the sphere that there was. That is the self-energy of the sphere. And then you will have one term that talks about how the electron interacts with that positively charged sphere, right? Expressions will actually look something like this. So for the first term, you will have a summation over discrete electrons. Why is this mixed color? Never mind. You will have an interelectronic repulsion term here. You write, I'll keep this open. I don't want to mess up the expressions. So basically you have an interelectronic repulsion term. Ri and Rj are their coordinates. You just, again, we did not want you guys to produce an exact analytical expression for these because that is practically impossible. Then you will have the energy of assembling the cloud that we talked about. So the omega was actually the space of the entire cloud, the cluster, in which the electrons were embedded and moving around. So you integrate over all of omega to get the energy. And then you have the term that talks about how the electrons interact with the cloud. It's fine if you have not given us the exact expressions if they look like this. If they make sense, we've given you marks. Don't worry.
What matters the most is if you have mentioned that for the interelectronic repulsion, you are getting this term. For the interaction between the positive clouds with itself, you are getting this expression. And for the interaction between the positive cloud and the electron, you are getting this expression, which is a mix of summation and integration. For the positive-positive interaction, it is a double integration. And for the interelectronic portion, it is just a normal
Summation.
Coulombic.
Now, for the second part, we gave you the molecular orbital diagram, right? So,
what you had to do was count the number of valence electrons in this thing, which is, if you count this, this is 40, I think.
So the first cluster is Al11 Mg2 minus. So Al has 3 valence electrons and Mg has 2. 11 3s are 33, 2 2s are 4, 33 plus 4 37, and a negative 38. Go back to the previous page. Now count here to fill this with 38 electrons, 2, 6, 10, 2, 6, 6, 8. The whole sum is 40. So where will you reach? You will reach here with 6 electrons. 2, 2, 1, 1. So it is 38. Now go to the next. No, previous. So first question we asked that which one will be more stable, the distorted one or the non-distorted one. So you have 6 electrons in your valence orbital. So if you fill it, so here we will get 2, 2, 1, 1. And here Yan-Ter distortion is occurring, which means that in order to stabilize itself, the degeneracy or the symmetry of the orbital is broken. So as you can see here, it is D5H symmetry and C1 symmetry. So the thing you should know that D5H is more symmetric than the C1. C1 has literally no symmetry, and D5H has 5-fold symmetry. And now if you fill it, you will get 6 electrons here, and they are at a lower energy level. Their energy is lower than the barycenter. And here you have no such thing. You have only the same spin direction. So in this case, due to the partial filling of the valence shell, this structure will be more stable because it has 6 electrons in its lower energy level after the splitting of this degenerate level, and this structure is nothing. And for the second part, if you go, Al11 Mg2 3 minus, it has 40 electrons. 40 electrons means the valence orbital, it is fully filled. So this thing will nullify. This effect will not be here. So eventually this structure, it will not show any distortion at all. So only it will show no distortion, so no distortion for that.
Also, one more thing we'd like to tell you guys is that pairing does not make anything stable. In fact, pairing increases the energy of the system because there's interelectronic repulsion. So if given the chance, it would stay unpaired. But what's happening here is a competition between staying unpaired or going to a lower electronic energy level, where this is winning. The energy that you are releasing out of going to a lower energy electronic level is making it more stable than if it were to stay unpaired. So if you've given us the reason that pairing does not make anything stable. If you guys have any questions. No? Cool.
So that concludes the brief thought round for Mimamsa 2026. I request all the participants to follow their team coordinators. We'll be heading off to lunch. And see you at 2 p.m. in NLH for the Bio Deep Thought round.